All right. Okay, so let's kind of pick up where we left off. The last theorem we had, I think, was 686. So let's hit that one. We noted last time we noted that if right exactness and tensor product, we know that. And in general, you don't get full exactness. And I'll look at an example of that in a moment. However, in the case that you get split exact, you know, you use harmony and the splits, then so does so if this splits, then the augmented series splits. I'll leave this mostly as an exercise, but let me just sketch it for you. Since there exists H from B to A, such that when I do F, then H, this is A. So there's an H that goes by. This. So now consider you already know that this much is exact. We also know this. The existence of the H above is an existence of this H tensor one below. Really, and also since doing F and H gives you the identity function on A, just check that F this is an easy check actually, that when you do the composition of those, you get the identity on this, which means not only is F tensor going to be 1-to-1, but it also means sequence splits. Okay. this. We give an example to show kind of the hazards. Let me start with example. Consider the short exact sequence. Consider the short exact sequence. Where I need to explicitly tell you how this works. Uh, okay, now I want this to be a short exact sequence. By the way, somebody explained to me why this, no matter how I dance around, there's no way that this sequence can split. Somebody tell me why. It is impossible. I'm gonna make a short exact sequence, but no matter what I do, I can't make it be split exact. Does anybody know? Using these groups. Right, that's correct. But here's a quick way to see it. Z4 is cyclic of order 4, right? If this sequence split ever, then that would mean Z4 is isomorphic to Z2, Z2, which is possible. Z2, Z2 has 3 elements of order 2 and one of order 1. This has 2 elements of order 4, an element of order 2, and an element of order 4. So it's possible. There's really kind of only one way to make an interesting short exact sequence theory. I have to take the identity to the identity. And this thing can't go to an element of order 4, right? You can't take an element of 2 to an element of order 4. You have to take it to an element of order that divides it. So my only choice is to go to 0 bar, in which case it's certainly one, or go to the element of order 2 here. Right. And this is the way that the subgroup embedding goes. And as you might expect, how do you go from here to here? And the 2 elements of 4 go to the element of order 2. This is basically quotient math. Notice that it is easy to see, since I've drawn little arrows, that the image of the first map is equal to the kernel of the second map. It's easy to see the last one's onto it. Questions? Now, here's the problem. I'm going to call this map 17. Now consider and this is like uh, Um, Notice the original map here, F is 1, 1, right? This is the zero map. And I'll show you why. Notice that, um, notice that the only possible non-zero tensor is 1 tensor 1, right? I agree, because everything else has a zero in it. Where does this go? Where does this induced map take the tensor 1, tensor 1? Well, this goes to what, 2 star? And of course, yeah, I didn't get the second. Everybody agree with that? But of course, this white element is a Z4. I didn't write it this way. Now, this white element is an element of Z4. So isn't this, oh, and I didn't make this clear, my bad. I'm tensoring over Z. This is 2. Right, because 2 star is 2 times 1 star, right? It's 1 star, it's 1 star. But this is a tensor, so I can pull that integer out. See, this is 2, 1 star tensor 1, R, and I can use the 2 in the second tensor. Of course, 2 times 1 bar is 0 bar. So, induced map, that'll be on to that is G tensor 1. Be on to. So we started with this short exact sequence, back to person 21. This is the zero map. Right? So there's pretty much no way that that is going to be 1 to 1. Unless, of course, this thing is 0. But again, it's this one we've looked at before. This is not 0. Right? So actually, you see a pretty marked failure of 1 to 1-ness here. And of course, what does that mean about these last two? The fact that F tensor 1Z is 0 map, what does it mean about Z4 tensor Z2 and Z2 tensor Z2? They're isomorphic, right? Because we know that this is onto, and the kernel of this is the image of the previous one, which is C. So in fact, it's isomorphic. Okay. Any questions on that? Okay, so Um. Right. Zero. 6, 8, 9, yes. I like this because this is a good exercise in, the tensor product, constructing, homomorphisms. There it is. Okay. Then, there exists R morphism. Usually had a second piece. So, well, okay, so how about some help from you guys? How do you think of might want to set this up? Okay, so, listen to this. A tensor R, it's too hard. Linear match, much easier. So, let's go. Here's canonical bilinear map. Takes the pair AR to A tensor R. We're on 6. Okay, so how about the pair AR? What do you think we should go to here? What's the easiest map? Get AR. What's the second easiest? How about that? All right. Just A, probably, I guess. That's not gonna work very well for you. Okay, so I claim that well, I guess the easiest is 0. Yeah. Right? Probably. F equals R A given by F of work pair A R A is my let me do a rough check of this. F of A1 plus A2, R, it's R, A1 plus A2. It's an R module. A1 R. So it's linear in the first coordinate. And this is almost identical. This is R1 plus R2. A, which is R1A, R2A, which is F of A, R1, F, A first. Good enough so far? And so TNR, yeah, P R, then F T A R is R T A. Rather unfortunate collection of letters there. And so it's bilinear. Okay, so what does that tell us? The magic of the tensor product says, hey, this is, I'm going to call this something. I'll call it G. This induces G bar such that G bar out of use. That is to say that G bar acting on the tensor A tensor R is AR. Great. So we have homomorphism F from given by, let me say such that F of AR is oops, for R, right? Okay. Notice that this just describes the homomorphism, what it does to single tensors. But actually for this one, it's good enough, right? But of course, once you know it does to single tensors, you know what it does everywhere. What's left? I want to show that this is an isomorphism, right? Okay. By the way, I think that we all should take a moment and just admire the beauty of the fact that just from this bilinear map, we get this homomorphism without having to worry about well defined this process look like. But now that we're done basking in the glow of that beauty, we need to show that it's one and onto, right? I think onto is pretty easy. Onto is straightforward. Somebody explain what's onto. Actually, I guess I call that Q bar. Okay, that's fine. My bad. I called it bilinear map F, and then I called it G and everything else. But we're going to stick with this now. We have a homomorphism, from A tensor R to A, such that F of A tensor R is AR. Can somebody describe to me why this is onto? Right. If A is an arbitrary element of A, then F of A tensor 1 is equal to A. Now, the one-to-oneness for this, and of course, tensor product is always kind of easier to control with respect to onto. The one-to-oneness is a little bit more tricky here. So what can we do here? Right? Here's the problem. Right? What does X look like? Crap. Here's what X looks like. Yeah, and that's junky, right? I don't like that too much. However, we can do some stuff to make our lives easier. Any ideas? Are we all in agreement that this is a mass? This is ugly, right? What do I know? I know that, f of x equals 0. So this goes to AR1, AR plus AR2, blah, blah, blah. How do I know that that has to be 0? It turns out that for this particular tensor product, things work out nice for us. It's my first step. How did I, Krista, did you take that thing? Well, notice that all the R's, I mean, the A's I'm kind of hosed with, but the R's are elements of R. And that allows me to slide them across the tensor, right? For example, R1 is R1 times 1, so I can slide it across the tensor. R2 times 1, slide it across the tensor. Everybody agree with that? And now that I've got this, how can I shorten it further? That's right. Notice that my second coordinate always 1, so I can actually collapse this like an accordion. In fact, not just if it's in the kernel, if x is in a tensor R, then what can I say about x? X is a tensor 1 for some a. This is a bit of beauty because what we've shown, this is all confusing to me. I don't know much, but I know that this big mess of things is in A. So what we've shown actually is that every element of this particular tensor product can be written in a very special form. It can be written in the form A tensor 1, right? Oh my goodness, that is going to make my life easy. So now, suppose x, which we write after doing whatever process we have, in form A equals 1, is actually in the kernel of f. Let's go back to our diagram. F A comma 1 goes to 0. What comes from here? Well, notice that notice that A comma 1 goes to A tensor 1, which goes to 0. And this goes to 1 times A, and so A is 0. Diagram. Right? Because A comma 1 goes to A this way, but it goes to 0 this way, so A must be 0. Hence, x equals A tensor 1 equals 0 tensor 1 is 0. And so F is 1. We already know it's onto, and so have a nice day. Okay, any questions on that? Let me give you an exercise. Use a similar diagram like this. This is just kind of a fun warm-up problem because I can do some more. This will be kind of the last piece of the puzzle that earlier example. I've made this claim a couple of times. Now, use a diagram like this to show that Z2 tensor Z2 is actually not zero. In fact, if you like, you can. This is isomorphic Z2. So with that information, see if you can set up an appropriate diagram with bilinear map and set it up to show that Z2 tensor Z2 is isomorphic to Z2. In fact, what you'll show later is actually, let's see if I remember this right. I think it's right. Anybody want to guess what that is? Just for fun. Good. Tensor the two, it's isomorphic to Z mod GCD. Okay. Here is a Ruby theorem. I am not going to prove this for you because I'm going to put it on the homework, but I'm going to talk a little bit about the setup. So even though I won't prove it completely, I'm going to talk about the setup. I might have to do the homework. This is an important piece of the tensor product. See how this is not. It's called adjoint associativity. But A, B, C, say homomorphisms. Well, it's an R model. The set of homomorphisms, right, this would be C. It's isomorphic to the set of homomorphisms from A. The homomorphisms B tensor C or B comma C. So this one is actually an exercise to do, but I want us to, just for fun, to kind of try to wrap our heads around this. And so, how would you even do this? So I'm going to try to help you set up the map. And I'm going to, because you're going to end up doing this for homework, I'll describe kind of the strategy. Goodness gracious. I always have to think about this quite a bit when I do it. So if you want to go from home R, A tensor B C into home R, A home R B C. You got to wrap your head around this. Okay, so let me take this apart bit by bit. What's your input? Well, your input to phi should be a homomorphism from the tensor products. Now, somehow, this thing has to be in home A, home B, C. Right? So this accepts an input of an A, right? Now this thing This thing should now, let's see, what is this? F, you started with this, P does this, and this becomes now, this should be a homomorphism from A to the homomorphism from B to C. So this should now, at this stage, be a homomorphism from B to C, right? So to this one, you plug in a B, and what do you suppose the output's gonna be? It would have to depend on F. How about this? So this is a homomorphism. At this point, you're a homomorphism from A to the homomorphism B tensor C. So this thing is now a homomorphism from B to C, where you put in B and you get this thing, which is in C. How would you go the other way? Let's call this. Goodness gracious me. So you start. Uh, this should be an homar. Where my input G everybody with me here? So pitchfork of G, your input here is a homomorphism. It should spit out a homomorphism from A tensor B to C, right? And my input G is a homomorphism from A, the homomorphism B to C, right? So this thing here is a homomorphism from A tensor B to C. So to define what this homomorphism does, all I need to do is tell you what it does with tensors. So what do you suppose this is? So this thing has to be a homomorphism from A tensor B to C. So you input A tensor B, your output needs to be in C, and I'm going to use the G somehow. So G takes the input of A, and now that's a homomorphism B to C, and then takes the input of G. And this is C. Now I bet you, if I hadn't made any mistakes here, that this is how this math works. What I would suggest you do when I finally ask you the problem is set these homomorphisms up by whatever means you need, diagram, show that you have R modulo homomorphisms. I wouldn't show one-to-one and onto. I would actually show that when you do capital phi and capital pitchfork, you get the identity. When you do capital pitchfork, you get the identity. That's the easiest way to do this, I think. Okay. Any questions? There. 618. This theorem, as I'm gonna say, is a little bit redundant because I showed you the tensor product, A tensor B is isomorphic to B tensor A. But I'll write this out anyway as it's in the notes. Then one. The direct sum of AI tensor B is isomorphic to the direct sum AI tensor. So in other words, this distributes just like it's a sum of product. And two from the other side. This is redundant part. Um, Let me show you this. So in other words, tensor product commutes with direct sum. In fact, for those of you that are fans of the categorical stuff, direct product, tensor product actually commutes with direct limit, and is in fact the unique right exact function that commutes with direct limit. Let me outline one. So what do we want to do to show this? I guess we'll probably make this. Right. So let's do so this is the canonical bilinear map. So I'll take a generalized sequence, comma B, and this goes brief the thing. It's the generalized sequence tensor B, just that element of the direct sum tensor B, and what would it go up here? What's that? Yes, right. It's a comma, right? So my two sets are the direct sum first set, and the second one is B. So the first coordinate is actually this element of direct sum. Right? Exactly.
He's asking about the element, he's asking about like the actual capitalized sets, isn't it?
Oh, yeah. Thank you. I'm not staring at the element. That's exactly, and let me clarify that. That's what I mean. There we go. Is that it? Did I answer? Okay. And where does this go? Well, this goes where the math is easy to take us. This AI tensor B. So this gives us the desired homomorphism. I call this G. I call this G bar. Now, it's actually fairly clear that this is on to see if you can check that this is an isomorphism. It's very similar to what we did last time. So that's your G bar is your desired isomorphism here. I can't resist the following corollary. So some of you said before, we did this section that you've done each product. How many have you done it when you're algebra, physics, things like that before? How some of you have? Are you saying that in the? So, what happens when you tensor two vector spaces? What happens to their connection? You might know. Tensor two-dimensional vector space, three-dimensional. It's six-dimensional vector space, right? And this follows from this result right here. So this might, towards up, something may have seen before, but it doesn't matter if you haven't. Six of them. Let F be free. And say F is isomorphic to the direct sum R. So rank F is equal to cardinal I. Then when you tensor F with B, this is isomorphic to a bunch of copies of B. Where the number of copies of B is equal to whatever the range of the free module is. And the proof of this is easy. So maybe I can handle it. My free module I can replace by the appropriate number of copies of um, that's what previous theorem gives us, that direct sum and tensor product here. And what's R tensor R B isomorphic to? Exactly, that's another previous result. This is isomorphic to B. And so this gives us the desired result, a bunch of copies of B, and the number is exactly rank of. Okay. Any questions? I'm going to give you one last, starting on this last section, before we get on to modules over PID. And this section will be very short. This is just really kind of introductory to the terminology and some examples. I'm going to give you something in the homework to deal with this as well. Does anybody know what it means to be flat? Anybody ever heard of this terminology? Definition. He said the R module, you know, it's flat. Yeah. Given any short exact sequence, 0, A, B, C, 0, corresponding sequence A tensor M, B tensor M, and the C tensor. Is also exact. So flat modules are nice. They're the ones that preserve short exact sequences. Anybody know a kind of module that's going to be flat? Yes. Well, yes, free your mind. Right, free modules are always flat. And in fact, flat is in a certain sense a generalization of free modules. We'll discuss it more next time. Questions? Questions? All right, well, we will see you all on next.